Stan Gibilisco here to talk about the design for an op-amp high-pass filter. Probably you would want to use such a thing at audio frequencies. The basic operational amplifier circuit, as we have seen, has an input and an output, actually two inputs, the non-inverting input, the inverting input. If you supply some feedback to the inverting input and apply the signal input to the non-inverting input, you will get an output that is in phase with the input signal, and you can adjust the gain of this operational amplifier by adjusting the value of this resistor. As the resistance goes down, the negative feedback increases and the gain gets lower. As the resistance goes up, the amount of negative feedback decreases and the gain goes up. Well, suppose now that we want to make a circuit that has a specific type of response in terms of output amplitude versus frequency. And suppose that we want it to look like this. More output as the frequency goes up, less output as the frequency goes down. They call a circuit like that a high-pass filter. And you can build them with coils and capacitors. They don't provide any amplification, but you can build them. They're unwieldy, bulky. The coils can be difficult to find, etc., etc. So what can we do to this circuit right here to make it act as a filter that will provide a response curve like this? Well, what we can actually do is connect a capacitor between the inverting input and ground through a resistor like this. Okay, now how does that work? What happens as the frequency varies? Well, as the frequency goes up, this resistance has no effect on the amount of negative feedback that gets to this inverting input. However, as the frequency goes up, more and more of this signal will get shorted to ground through this capacitor. The resistor here just serves to prevent circuit problems that would result from not having it. It's sort of a buffer resistance that you can include to regulate the amount of steepness in this curve. But it works best if there's some resistance here. As the frequency goes up, then the negative feedback here remains the same, but more and more of this signal gets shorted to ground, so that tends to reduce the negative feedback. Less negative feedback, greater gain. Okay, so there you go. There you have it. Contrary-wise, as I try to get rid of all these little blobs, let's just leave it in. It's pretty. As the frequency goes down, what happens? This amount of negative feedback remains the same. This amount of negative feedback, however, decreases, so less and less of this signal gets shorted to ground, and the net negative feedback increases, driving the gain down. That's because of this capacitor. Remember, its reactance increases as the frequency goes down. So as the frequency goes down, less and less of the negative feedback will get shorted out, so in effect you get more and more negative feedback. As the frequency goes up, the reactance of this device, the opposition that it offers to alternating current, goes down, so more and more of this negative feedback gets shorted to ground. That results in less net negative feedback and greater gain. Kind of convoluted, but the circuit is simple enough, wouldn't you say? And no bulky coils to deal with, and you also get the bonus of having some gain through this operational amplifier. So they call that an active filter. The reason they call it an active filter is because it does require an external source of voltage, not shown, in most diagrams like that. And also the active filters produce gain. Passive filters, like you get from just a coil and a capacitor, do not produce any gain. Moreover, by tweaking the values of these resistors and capacitor, you can actually adjust the frequency at which this curve is the steepest, in the middle of the curve right here, and you can also adjust how steep that curve actually is. Kind of cool stuff, huh, for such a simple little circuit, little chip, little integrated circuit about the size of a baby's thumbnail. Stan Gibilisco signing off. Until next time, so long.